All right, good morning, everyone, and thanks for coming back today. We have the third and final, at least for this round, installment of our series of Mankei Tsang seminars. So please join me in re-welcoming Mankei to tell us about one waveform.
Thanks for having me again. This talk is about sensing with a dynamical system. Might have heard a lot about fundamental studies in quantum metrology, sensing. A lot of theoretical studies focus on toy model. You assume there's a qubit, you assume there's some simple phase shift, and then you do a measurement. You look at a sensor in real life, like LIGO, or look at magnetometry. The situation in practice is a lot more complicated. First of all, usually you need to deal with a signal that is time dependent. Gravitational wave is not just one phase shift, it is a time series that we are going to call a waveform. There's a continuous input field. It's not just a single shot measurement. There's some continuous input field going in to your sensor. And also you are doing a continuous measurement of the output field. It's a field, so it's not just one simple system, but it can have many modes, and then you have to choose the basis that you are measuring in, and also choose the type of measurement that you are doing. For a lot of these systems, we can assume that the Hamiltonian is this following form. Here's the unknown waveform. For this talk, I'll just assume that the waveform is a scalar, but it's a time series. So x is a scalar function. It's coupled to the sensor through an operator that I'm going to call the generator. And then everything else, I'll just include it in the Hamiltonian as the rest of the Hamiltonian. Of course, it can be very complicated, but this is the general form. For example, if you look at LIGO or optomechanics, x of t is just classical force, again, a waveform. This generator is the mechanical position of some mirror that you hang in your observatory or in optomechanics. The measurement could be optical homodyne or photon counting, but continuously. In the simpler case, we will also consider optical interferometers, so that you don't need to worry so much about the mechanical degrees of freedom. Then we can think of the classical waveform as some phase modulation that is time varying. The generator, in that case, is just the photon flux. So in this case, think of a continuous optical beam, and then there's some continuous phase modulation that is applied to your optical beam. Then the generator is the photon flux. Many different types of measurements you can do. And last but not the least, you can also think about atomic magnetometry, where you have a magnetic field that you want to sense. It's coupled to some atomic spin operator, and then again, you are doing some sort of optical measurement. Of course, if you are dealing with a magnetic field, it's a vector in general. That has its own complications, but I'm not going to talk about that case. I'm just going to focus on the fact that the waveform is time varying, but scalar, just for simplicity. There are a lot of fundamental questions that you can ask about this problem. Basically, you can just go to Hellstrom's book and repeat all the calculations in terms of what would be the fundamental quantum limits to how well you can estimate or detect this unknown waveform. That's one big question you can ask for any measurement. So that's the basis of quantum estimation and detection theory, of course. Once you've found the quantum limit, then you need to come up with a good measurement that would approach these limits. So that, I suppose, would be what the experimentalists would be most interested in. Is homodyne good enough? Do you need to deal with a lot of other noise sources like measurement back action noise? Perhaps photon counting would be better. And also we are dealing with an optical field. So not just one mode. So you also have to worry about which optical modes or which optical bases that you are measuring. And finally, you can ask, what is the best data processing that you can do? Well, this part is relatively simple because ultimately, once you've done the measurement, you've got some measurement results, you're basically doing classical statistics. Of course, the noise comes from the quantum measurements and all that, but ultimately, once you've got the data, the unknown waveform is classical, and then you just need to do your classical statistics. In that case, there are still a lot of non-trivial questions about what is the best data processing, do maximum likelihood, do Bayesian, especially because your measurement is a time series, it's a little bit more complicated. Many other questions you can ask, what is the best input state that you put into your sensor? Or perhaps you can even be more ambitious and say, I want to redesign the whole thing. I want to optimize the dynamics. I want to apply some control to my experiment. But these are topics that I don't have time, or I don't have anything interesting to say about these. So let me skip that. Going to focus on 3 specific problems. The first problem is, well, this is the unknown waveform. Let's estimate it. That's what we call waveform estimation. That's the most obvious task you can think of. What I'm most excited about is the second task, noise spectroscopy. Here, x of t is a stochastic process. We assume that it's a stochastic process. We are not estimating x of t. We are estimating its statistical properties. Let's assume that it's a stationary process. It has a power spectral density. But there are some unknown parameters for the power spectral density that you would like to estimate. So it sounds kind of similar to waveform estimation, but it turns out to have a lot of surprising results. I'll talk about that later. If I have time, I'll talk about the detection problem. Probably I won't have time to talk about the detection problem, but we'll see. So these are the 2 problems that I'll focus on this talk. Let's start with the first task. Estimating waveforms. The first thing you need to realize is that this is a function of time. So in each time series, it actually contains many, many parameters, or effectively infinitely many parameters. So it's not just one number anymore, but it's a function. When you're dealing with so many parameters, well, all the techniques that you know and love in basic statistics are not going to work anymore. Maximum likelihood, unbiased estimation, Kramer bound, all the simplest tools that people use in statistics don't work. Why? Because, well, you have so many parameters and they are fluctuating in time. They are random. All these basic techniques assume asymptotics. They assume that you have a parameter that is static, that doesn't change in time. You can do multiple measurements of the same parameter. Okay, so all these techniques rely on some sort of asymptotics, that the parameter stays constant in time. You do a lot of observations, and then some sort of asymptotics give you nice results concerning maximum likelihood of the Kramer bound. But when you're doing waveform estimation, it doesn't work anymore. It is changing in time all the time. And also the waveform doesn't repeat itself. Well, okay, there's some gravitational wave coming in. You cannot expect the exact same gravitational wave to come in again and again. And so the asymptotics just doesn't work anymore. Well, what do you do then? Well, in classical statistics, we know, since the Second World War at least, that when you deal with a waveform, you should try not to use maximum likelihood, but you should try to use Bayesian statistics. So people have known this since the Second World War. By Wiener, for example, he has written a book on this. How do you do estimation of a waveform? And of course, Russians have done this earlier. And it's known, this is why we teach statistics in electrical engineering with radars. And we realize that the best way of dealing with this problem is to assume that x of t is a random process. The mean square error, we don't assume a mean square error as a function of the unknown process. We also take another expectation, assuming that there's some prior probability measure for your waveform. So we are going to do Bayesian. Okay. Of course, if you're a theorist, you say, well, I want to do minimax. That's what people do in cryptography and security, in computer science, and then you don't need to assume a prior. You look at worst case error, but well, I'm not going to talk about minimax at all because the math is really difficult. Usually, I think all people who do minimax statistics are basically mathematicians. If you're not a mathematician, you can try minimax yourself, and then after a few weeks, you would just come back. So Bayesian is good. Huh? Okay, now we need to deal with the quantum dynamics. Again, the system is a dynamical system. Well, we know from open quantum system theory, we know how to model continuous measurements. If you think about a continuous field going into the system, you're doing continuous measurement, there's a big formalism of open quantum systems that you can use to describe the problem, basically using a sequence of completely positive maps and Krauss operators, all that. So you can use that approach if you want, but it turns out to be very inconvenient to use because when you try to calculate quantum bounds for these systems, it becomes very difficult mathematically to apply all these Hellstrom bounds, Cramér bounds, or Bayesian bounds to the formalism of open quantum system theory. So we use a different approach. Basically, what quantum information theorists would like to call going to the church of the larger Hilbert space. That turns out to simplify the problem a lot. Instead of thinking about open quantum system theory, we assume that we include all the degrees of freedom that is relevant to the problem. In that case, basically, we can assume that the initial state is pure. We don't have to worry about all the Krauss operators, completely positive maps. We'll just assume that all the dynamics is described by unitary evolution. That turns out to be possible, always. And finally, in practice, you're doing continuous measurements at the same time as the waveform is coming in. But in quantum information theory, there is something called the principle of deferred measurement, that we can actually use an equivalent model of final measurements at the final time to reproduce the statistics of a continuous measurement. In other words, basically, in principle, in theory, it's always possible to replace the open quantum system theory with pure state unitary dynamics and a big measurement at final time. And according to the church, it's always possible. So now everything is pure. The unitary is just one big unitary with the Hamiltonian that I just described before. And now the problem becomes, yes, sorry.
What if there's, I guess, measurement that changes
the dynamics?
That changes how you do subsequently.
Yes, that's great. Yes, because you can model it as a unitary. So it turns out that it's always possible. Even if you do measurement and then you do feedback, right, you can remodel everything in terms of unitary, in terms of, C0 gates and all that. So the nice thing about this formalism is really that you can, everything you can do, anything you can do, you can model it using this sort of. Of course, there's a price to pay. I'll talk a little bit about that later, but in principle, it's possible. Okay. So, well, now that everything is pure and unitary, we can apply those theory in Hellstrom's book to the problem. To get a simple result, we have to make some assumptions. Unfortunately, what I call tasteful assumptions, so that you get simple results, but not too simple. We want to include the essential dynamics and essential characteristics of the problem, but we don't want to include everything and actual LIGO. Otherwise, the result is going to look too complicated. So we assume that basically the quantum system has stationary statistics so that we can describe everything using power spectral densities. That's not too bad if you're looking at optomechanics and LIGO. If you go to any talk by optomechanics people or LIGO people, they like to talk about power spectral densities, right? So that's okay. We can make that assumptions. They do the same thing in their system, so we can do that. For x of t, we said that we are going to do Bayesian. We assume that it's a random process. So we are going to assume that it's Gaussian, a Gaussian random process. We are going to assume that it's stationary, so it also has its own prior power spectral density. And also we assume that there's a long observation time relative to all the coherence times of the problem, so that we can express basically everything in terms of frequency domain quantities. So you make all these assumptions, you apply the formalism, you work on this for about a month. That's what I spent, how much I spent my time. And eventually we got this result. A lower bound on the mean square error. So the error fundamentally cannot go below this lower bound. As a bonus of using the Bayesian formalism, the bound actually works for any bias or any unbiased estimator. So you don't have to make that assumption if you don't want to. As this, at least I can write the equation on one line. So it's relatively simple. This is the important quantity. It's the power spectral density of the generator in the Heisenberg picture. It just turns out that if you apply the formalism to the dynamical system, this quantity just pops up in your bound. So the Heisenberg picture somehow naturally comes up in the problem. So it looks, the integral looks kind of scary, but roughly speaking, it's the 1 over the inverse of this power spectral density of the generator. If you compare it with the simple case of the quantum Kramer-Rao bound, you see a similar feature that it's, the precision is 1 over the variance of the generator in this very simple case. And in the dynamical case, we just have a generalization of this uncertainty relation, but it's just in terms of the power spectral density of the generator. So again, for example, in optomechanics, the power spectral density is just the power spectral density of the mechanical position. Or in the, when you're estimating the optical phase, this guy is just the power spectral density of the photon flux. And also the bound has another term that depends on the prior power spectral density of the random process. And that is just representing the prior information that you have about the waveform. Okay, this is a little bit mathematical, but let's just talk about what you need to, yes, please.
Can you give me some intuition for why the order of the 1 over, like why it's not integrate the denominator and then take the reciprocal instead of parameters? Because I normally think of, so you're saying you normally think of adding the Fisher information.
Right.
There. So I would have naively thought I would integrate that denominator and then take the reciprocal, but here it's the opposite.
I don't have I don't have a good answer for this. It just somehow it appears this way. Yes.
So you're expressing kind of the mean squared error as an integral over the spectrum. Is it also fair to say that if you're only caring about estimating one frequency component of the waveform, because the bound is the same without the integral?
It's a great question. I think you have to include something else. If you want to generalize this bound, you have to include something else in the numerator. I'm not too sure if it's just this guy without the integral, but it's a good point, probably. But yeah, that makes sense, right? I think it is, but I don't remember exactly. Okay, that's a great question.
Yeah, I think the question in practice, you do a finite experiment, right? You got to go through the infinite experiment. So there's one finite duration and so forth.
Yes, the problem is that we are dealing with a random process. So the random process inherently has its own correlation time. And that correlation time, and we are assuming that the experiment is much longer than that correlation time. So this is why the mean square error, even though your measurement time is long, the mean square error is not just zero, because the random process itself sets the effective time at which you're doing the measurement. Not sure if I'm addressing your comment or not.
Well, I just wonder if you have to integrate the infinity.
Right, yes. So I think this term is going to be finite. It's going to be finite. So for example, if you know that the power spectral density of x of t is equal to 0 outside some band, then that would set the limits of the integral. Okay, so the bandwidth of the random process sets the limit to the integral. But even if it's a soft bandwidth, like if in the frequency domain, if it looks like this, the integral still converges. Yes.
I'm actually now confused on what this is looking at the mean squared error, because the time dependent process. So is this the mean squared error at a particular time, or somehow a long time average of the mean squared error, or?
Right. So it turns out that when you're dealing with some random process, the estimation error goes to a steady state. So imagine that you're tracking an airplane, right? And it's, fluctuating. It turns out that when you make all these assumptions, there's a steady state estimation error of tracking.
So is that, so when you said there's steady state estimation error, it means that the mean squared error of the position at a particular time goes to a steady state in the 1/10.
Yes. So for example, if you have a long random process, you're estimating the random process at a particular time somewhere in the middle, then it turns out that somewhere in the middle, there's a steady state. Yes.
Two questions. Can you say anything about estimating multivariate trajectories? And the second question is, so this equation, again, is integral in the frequency domain.
Mhm.
And I think the interpretation of frequency domain is relatively straightforward, as we're describing. It's basically for each frequency component of extra information and previous information. Is there a way to think about this in time domain? Like as some kind of convolution?
Time domain, we did this in the frequency domain because we want to relate this to what these optomechanics LIGO people have been doing. They have been using power spectral densities. There can be a time domain formalism of all this, but I didn't have. The problem is that I did this and then I moved to Singapore, so didn't get the chance to work on this any further. I cannot keep working on LIGO stuff in Singapore. So, but yes, in principle, I think it's possible to generalize this or rewrite this in a time domain formalism, but I just didn't have time or resources to do it. Your first question is about
Multivariate.
Multivariate, like for example, if you have a magnetic field,
For example.
right? It's possible. We can definitely derive a bound. Whether the bound is tight or not, there are additional questions because of, you cannot measure observables.
Parameters if they're not.
Right, yes. So that's a great question. I really haven't got the hang of multivariate or vectorial estimation yet. I don't really have a good insight about that, but it's possible to derive a bound. Okay, all right. So now we have the bound. We need to tell the experimentalists what do they need to do to reach the bound. Well, let's assume that you're putting in some coherent or Gaussian state light with some stationary statistics. Remember, again, now the input field is continuous. So you need to worry about not just the variance of the Gaussian statistics, you also need to worry about the power spectral density of your input beam. But let's assume that it has power spectral density that is stationary and also the statistics is Gaussian. If you are working on LIGO, the first thing you need to do to achieve this bound is to remove the radiation pressure noise. So it turns out that if I have time, I can talk more about this, but it turns out that radiation pressure noise is a significant problem now in LIGO. To achieve the ultimate limit, you need to make sure that this noise is negligible or removed. Okay, there are many different ways of doing this. Again, if I have time, I'll talk about this, but let's assume that, okay, that's removed. There's no radiation pressure noise. And then things become a little bit simpler. Just do homodyne measurement. It turns out that it's good enough. When you do homodyne, at the output, roughly speaking, you will see some signal plus some noise. And then the noise would have its own power spectral density, of course. And last but not the least, you need to do classical data processing that is optimal. We are dealing with the Bayesian problem. So we know that the minimum mean square error is just the conditional expectation. In engineering, this is called smoothing, but it's not so important. The important point is that once you do this conditional expectation, you can calculate what is the steady state mean square error of your output is given by this expression. It looks very similar to this expression here for the quantum bound. So assuming that you do all these, everything is perfect, there's no extra noise, all the noise comes from the input field, then the noise floor of your homodyne turns out to be equal to this quantity. So then you are done, okay? But this is assuming that everything is perfect. There's no loss, there's no other sources of noise, and even radiation pressure noise is negligible. Okay, so that's a nice story. We managed to convince Furusawa's group in Tokyo to do a proof of concept experiment. Continuous input beam could be squeezed. There's a very classical mirror that reflects the light. So it's very classical. It's very massive. So you don't need to worry about radiation pressure noise or anything. And then the measurement is just adaptive homodyne. And then the estimator is some smoothing algorithm. So they managed to show experimentally that the final error is very close to the quantum limits. And also there's a more recent experiment applying similar techniques. They don't call it smoothing because the smoothing theory is something I invented in 2009. And Klaus Mulmer basically reinvented everything and called it by a different name. And then they collaborated with Schall's group to do an experiment for magnetometry, but it's similar ideas.
So you might what's the smoothing idea?
Smoothing is basically the idea of taking the output from your homodyne as a time series. Okay, and then I do a conditional expectation. Conditioned on my measurement record, I want to ask what is the conditional expectation of the unknown waveform, x of t. So expected value of x of t conditioned on my measurement record. So we know from Bayesian theory that this is the best thing to do to minimize the mean square error. It's called smoothing because when you take the output, you want to do this conditional expectation. It involves some time series smoothing or filtering of the time series. But ultimately, it's really just conditional expectation. Okay. Anyway, so all right. Let's see how much time I have left. All right, okay. So not much. So I'm going to skip. So I think for people in this area, they also very often raise the question that some Russians discover similar things like 20 years before us. But I just want to say that their so-called energetic quantum limit is more heuristic. It doesn't explain everything. And also, of course, we are using the church of larger Hilbert space approach. We assume that you can measure everything. But that's of course not true in practice, but there are techniques to derive tighter bounds, including the effect of loss. Okay, this is the part I really would like to talk about. Now we are going to talk about the second problem that I mentioned earlier. This is a little bit different in the sense that we still have a random process here, the waveform, but this is not what we are ultimately interested in now. We assume that it comes from, again, it's a stationary random process. It has a power spectral density. And ultimately, in this problem, noise spectroscopy, I would like to estimate unknown parameters of the power spectral density. This is now a different problem. Some examples is that instead of estimating the gravitational wave itself, maybe you want to estimate some background of gravitational wave. It's now a stochastic process. I don't care about the individual waveforms. I want to estimate parameters of its power spectral density. So there's a different problem. Many other problems in optomechanics that you can think of as a noise spectroscopy problem, or in magnetometry. Sometimes you are not tracking the magnetic field itself, but you want to learn about its power spectral density. Okay, the nice thing about this problem is that the unknown parameter is now pretty much static. Okay? Even though the waveform is changing, the parameter that is influencing the power spectral density is pretty much static. We can go back to maximum likelihood Kramer-Rao bound, all these standard tools and statistics. And I'm going to focus on interferometry as the example. We'll calculate the quantum Kramer-Rao bound for this problem. So this is the Kramer-Rao bound. It's expressed in terms of 1 over the Fisher information. We managed to calculate an upper quantum bound. It's not exactly the quantum Fisher information, but an upper bound on the Fisher information. Has this scary looking expression here. The expression is not too important, or it's important theoretically, but not so important for the purpose of this talk. I'll just give you a simple example. Let's assume that the power spectral density, let's assume that we are doing phase noise spectroscopy. So you have a continuous optical beam. There's some phase modulation on the optical beam, and we just want to estimate some parameters of the power spectral density of the phase. The generator is the photon flux. Let's assume that this guy is flat. And also assume that the power spectral density is flat. Also for the phase, is flat with some bandwidth. And the unknown parameter is just the height of this power spectral density of the phase. Okay, it's just a very simple example. This is the quantum bound on the Fisher information. Notice that there's log-log plots. There's Fisher information normalized by the bandwidth and the time, integration time. This is basically the parameter itself. This is the quantum bound. You cannot violate it with any measurement. The interesting thing, if you compare it with the Fisher information for homodyne, is that there's a huge gap between the two. Again, remember this is log-log plots, so this gap is huge. So that's surprising, because if you are the Russians and you look at energetic quantum limits, the Russian limit that I talked about earlier, then you would say, oh, homodyne would be the best for anything. But it turns out that their bound cannot explain the fact that the quantum bound is so much higher than what homodyne can do. Of course, if you are an experimentalist, you ask, how do I achieve this bound? And it turns out that there is a relatively simple measurement that you can do, which is spectral photon counting. Again, assume you have phase modulation, some random process modulating the phase of your optical beam as you're trying to estimate parameters of the power spectral density. The optimal measurement is just take the output field, separate it into multiple spectral modes using a diffraction grating, for example, or a resonator array. So now you can measure each spectral mode individually and then do photon counting. This just spectral photon counting, or just how you would do spectrometer conventionally, right?
Sorry, I think so. We are not using a single mode laser. I'm trying to see what kind of version you have.
Right, you are doing a continuous wave laser,
One with
CW laser with one frequency.
one figure.
But the phase modulation is now time varying. So the output field is now broadband because the phase modulation is in the time domain, is changing all the time.
Okay.
So the output is now broadband.
Okay, so there's some small modulation in the
Yes.
CW frequency, and you want to separate these frequencies and then.
Yes. So at the output, yes, that's a great question. Input just one frequency, right? But at the output, you have phase modulation that is random. So at the output, if you just pass the light through a spectrometer and you measure the spectrum, you will see something like this. You see the input frequency, but then you see a broadband modulation that is symmetric. Okay, it has to do with the fact that you just have phase modulation. So you see symmetric sidebands. Yes.
I guess you're still paying a price. And is it fair to say that the price you're paying in doing spectral photon counting versus homodyne is that you lose the information about the relative phase between different spectral photons?
That's
Let me I guess be more specific. So this is kind of a different problem than estimating the waveform. It's to estimate the waveform to know not only the spectral density, but also the relative phases of different sinusoidal components. So this only allows you to measure something stationary where you discard the phase.
that is one, I would say it could be a good way of understanding this, but I'm not sure. Because if you're dealing with a stationary random process, basically in the long time limit, you can assume that the different spectral components are not correlated to begin with. So I'm not sure if there's any information to.
But that's only under that assumption. So the point is, if you didn't have that assumption, you might also want information about the phase. If you say you don't need that, or it's stationary anyway, you can put more effort into getting out spectrum.
Right, but throughout this talk, I always assume x of t to be a stationary random process. So I'm not sure. The point is really that you can only measure the power spectral density, right? You are measuring x squared. You don't have the sign information about each component, right? Each component, fundamentally, if you have look at x of t, you do Fourier transform, look at each component of the waveform in the frequency domain. This technique only gives you something like this. X squared. You lose information about the phase of this guy. I think that's the better way of describing this. Does it make sense?
No, I think we're saying this.
Okay.
But then isn't it really analogous to a simple one mode squeezing situation where you say if what I really want to know is power of the photon number, it would be silly of me to measure X and P. I'd be learning about an irrelevant thing and giving something up. The only thing that surprises me is I would have thought you'd lose something like a factor of 2 by making that extra effort. Here, you're losing orders of magnitude.
Yes, that's the surprising part. I'll try to explain. Okay, so why is that's nice. We discovered this back in 2016. And as I mentioned in my first talk, this idea was picked up by Caltech scientists. They realized that also by doing spectral photon counting instead of doing just the usual homodyne that LIGO does, you can have much enhanced visual information, much enhanced estimation error. So this is a recent technical paper that they posted in terms of a more detailed technical analysis about the enhancement that you can get by applying this idea to Michelson interferometers. So they didn't tell me. So I just saw this paper and I read it and I realized, oh, it's our idea. That's really nice. I wish they just told me. But anyway, they did, yes, right. But I wish they just sent me an email and say, well. Anyway, they did cite my paper, so that's nice. So they look at photon counting, look at stochastic noise-like signal and measuring the Fourier-like basis, and then you get much enhancement. So they have started a project to build a new experiment at Caltech. They are going to build a Michelson interferometer, but instead of doing homodyne, they are going to do spectral photon counting. And it's not detecting gravitational wave anymore. They are trying to detect signatures of quantum gravity. I'm not sure how that works, or whether it's going to work, but we should be ambitious. But anyway, that's what they are trying to do. Okay, now I'll come back to this question, why the enhancement is so large. Let me start with a very heuristic explanation first. Look at Michelson interferometer and assume that there's no noise at the beginning. Let's assume that for now, X is equal to 0. Everything is perfect. And we measure the dark ports. Imagine that you're doing photon counting at the dark port. So if everything is perfect, there's no signal. It's just dark, right? It's perfectly dark. And if you're doing photon counting, you just measure 0 photon. And remember, what is the variance of 0 photon count? It's 0, right? So perfectly quiet. Well, of course, sometimes you get some signal coming in. So the signal is Poisson, so you get some variance. But then the variance of Poisson photon counting it just scales with the signal. Now think about what if you're doing homodyne instead, you get vacuum fluctuations all the time, even when there's no signal. Even when there's no signal, I'm detecting the output, I still get vacuum fluctuations. So of course, sometimes you have signal coming in, but the variance is dominated by this vacuum fluctuation. So that is a very rough explanation of why photon counting is better. Okay. But I should stress that this is very heuristic because you look at this explanation, it doesn't explain why homodyne is good enough for estimating the waveform. Right? I mentioned at the beginning of the talk that homodyne is good enough for estimating the waveform. So this explanation is really ad hoc that I go back and then say, oh, that's the picture. But at the end, you still have to do the proper calculation to see that there's a huge difference between estimating the waveform itself and estimating the average energy of X squared. So it turns out that the different measurements. So the intuition is exactly as what Ephraim described earlier. If you're estimating X squared, the type of measurement that you need to do is very different from estimating X. I'll give you more examples about similar problems where photon counting is much superior to homodyne or heterodyne, so that you'll be a bit more convinced that this is a similar effect. First of all, detection of thermal radiation. Imagine that you're doing astronomy, you're measuring some light from some stars. is really well known that at optical frequencies, doing photon counting is much better than doing homodyne or heterodyne or any kind of linear detector that you'll be doing. This is well known since the 60s. It's the reason why they have to invest all this effort into transition edge detectors, single photon detectors. Think about heterodyne or homodyne detection, right? People can do 99% efficiency already. Why don't they just do that? It's really because fundamentally, photon counting is much better than doing linear detection. Another example is, I think I'm going to skip this example. I think I'm running out of time. Maybe I'll just talk about it. In physics, in quantum metrology lately, people are very interested in detecting dark matter. Well, you don't know what it is, but one model is that the dark matter are axions, which means that there's some interaction Lagrangian. They don't use Hamiltonian, they use Lagrangian, that couples this axion field to electromagnetic degrees of freedom through this sort of interaction Hamiltonian. So what they do is that they have a microwave cavity at cryogenic temperature. They apply a very strong static magnetic field and hope that through this interaction Lagrangian, the axions, the dark matter, will be converted into microwave photons. And if you detect some microwave photons, then of course you do some characterization, and hopefully you can claim that this is dark matter or axions. So on the microwave side, the axions are doing random displacements in both microwave quadratures so that you see thermal microwave coming out. In this problem, people also know that photon counting is so much better than doing linear detectors. You have to do this, or people mostly do this at the microwave frequencies. So now people are investing a lot of effort into improving their photon counters at microwave frequencies.
So you got me really confused. I could have sworn that just because of thermal noise issues, people like the superconducting qubit folks were specifically showing that they could use homodyne to effectively do single photon counting, because they couldn't do direct single photon counting. Am I just wrong about that, or is it somehow?
I'm not exactly sure which, right, but I'm not sure about the specific.
The idea that photon counting is better than homodyne, is that under the assumption that there's no background technical noise we have to worry
That's
about?
true, yes.
Become better again once you have a small signal relative to the noise.
I would say that because there's such a fundamental advantage between photon counting and linear detectors, that even if you have a little bit of background, there's still a significant improvement. It's only when you have really strong background that these two techniques become comparable. But the reason, yes.
Maybe what Ephraim is getting at is if you have detector noise, then homodyne will become better when you're using kind of the amplification of the homodyne.
Probably, yes. Right. So yes, if you have a lot of excess noise, background counts, then it's true that these two techniques are not so much different. Yes.
Maybe a bit confused. So for the microwave, for the second case, right, is axion detection for microwave frequency. The thermal noise be an issue? I mean, what can we?
Right, they put it in cryogenic temperatures.
Oh, okay.
So very low temperature, so that with if everything is good, you don't really see thermal photons coming out. Right, yes, but this is fundamental. It's really for the same reason that people don't do heterodyne or homodyne when you do optical astronomy. So you expect that even with a little bit of noise, it's still there's still a fundamental advantage of doing photon counting. So in our case, it's a little bit different in the sense that we have a coherent input. All these previous examples don't have a coherent input. And also we just have random displacement of one quadrature, not both quadratures. So in hindsight, this problem that we study is similar to the other ones, but a priori it's hard to tell. And of course, last but not the least, you look at incoherent imaging, you see random fields, you see randomly displaced photons, and it also turns out that if you measure in the right basis, you get much enhancement. So all these examples turn out to mathematically be mathematically similar in the sense that photon counting or measuring in the right basis gives you a lot of enhancement. Okay, let me just talk about this and we can finish.
So when you say lots of enhancement, so what's how we quantify it? What we mean, it's exponential enhancement.
It's sort of like this. In terms of Fisher information, remember Fisher information is the inverse of the Kramer outbound for the mean square error, right?
But radical.
Exactly. When you're doing homodyne in this example, this guy is basically proportional to the parameter squared itself. But this guy is a constant. Of course, this is a quantum limit. So in practice, you would be below it. But the hope is that when the gap is so large, even with some imperfections, you still get a lot of improvement.
So bigger can be arbitrarily small, you can have arbitrary
Exactly.
action.
Yes. And in practice, theta is very small, right? You don't expect dark matter to interact strongly with anything. And for most experiments, theta is very small anyway. This, roughly speaking, this regime is when your noise is dominated by photon shot noise. And this regime is dominated by when your noise is dominated by x of t itself. Remember, x of t is a random process, right? So the randomness of x of t also introduces its own noise. So when you're dominated by noise from the source, then the two techniques are basically the same. But when your noise is dominated by photon shock noise, then there's a huge improvement. Okay, I think this is a good point to stop. Let me just talk about the one last thing. Of course, so far I've been talking about coherent state input. Of course, the LIGO nowadays also do squeezing. Then the optimal measurement also needs to be modified. What we discovered very recently is that at the output, you cannot just do spectral photon counting. The optimal method is to do unsqueezing first. So you look at the dark port of Michelson, you unsqueeze the light first, and then you detect it using spectral photon counting. Then it's the optimal measurement. One common question I get is that if you do unsqueezing, are you going to undo all the enhancement due to the squeezing? But that's not true, because if you look at the phase space, let's think about squeeze input. This is the quadrature that the Michelson is modulating. You do squeezing here. Look at the output after before unsqueezing, after the Michelson interferometer. There's some displacement due to the signal. Okay. Now, what the unsqueezing does is not only to restore the squeeze quadrature into the coherent state value, but the unsqueezing also amplifies the signal. Okay, it's just stretching everything in this direction, So the unsqueezing actually amplifies the signal. But now you're dealing with a coherent state at the output. So now you can do spectral photon counting. Anyway, there's some recent similar ideas by other groups. So now you can perhaps go back to all these examples and think about whether you can use squeeze light to improve your dark matter search, for example, and what would be the optimal measurements. So that's an exciting field. Okay, I think I'm going to skip all of this. And again, come back to my favorite quote. yes, these things are difficult, but well, if you're a theorist, you know, you have to do it first, right? You have to do it before everyone else, so that hopefully, you know, after 50 years, you know, before you die, they can do the experiments. So eventually, hopefully, people can do this. Okay, all right. Thank you so much for your attention.